Alright, hello everybody. I just updated the description of the video to reflect what we're going to do today. So today we're going to be looking at libint. Let me hop over here. Libint is a C++ library. As the description says, it's a high-performance library for computing Gaussian integrals in quantum mechanics. So if you remember from last time I did a stream, we were working on some Hartree-Fock code. So if I hop over to my HFRS file module, you'll see that we coded up a working Hartree-Fock routine, but as you'll probably remember, we spent most of our time loading things from files. So we loaded all of the integrals, the kinetic energy integrals, the overlap integrals, these attraction integrals. We just loaded these straight from a file. So what we'd actually like to do is compute some of those using real basis sets. And that's going to open the door for us to do all kinds of stuff in the future. So we can do stuff like, we can actually do a geometry optimization ourselves, or we can, what I really want to do are semi-empirical methods. So once we have a working Hartree-Fock code with real integrals, we can start throwing away some of those integrals to do semi-empirical methods. So the purpose of today, I guess I need to make this bigger, right? So what I've done is I have cloned libint, and that's what we have open over here. So I'm inside their tests Hartree-Fock directory, and they actually have this main function that's one of their tests, and we're going to use as a guide basically to libint. Because this is just a simple Hartree-Fock code like we have, you'll see right away we're going to translate the definition here of computing the nuclear repulsion energy so that we can get rid of this to-do we left before. And then we'll dive straight into creating a basis set. So you'll see right here. Yeah, and I think I have my LSP all set up. Yeah, so I can actually... Okay, I do have to search for it. It jumps to the definition, not the declaration, which is kind of annoying. Probably, let's see. Go to declaration? No, alright. Whatever, it's fine, we'll make do. So we're just gonna start going through here. And I've tested it a little bit. Like I can actually click on shell, and it'll take us to the definition of that. So we're going to start working through this. Looks like the editor is performing well for me, which is good. Very good. It should be smooth sailing, hopefully. And we'll see how far we can get with that. So without further ado, let's start writing some code. The first thing, as I mentioned, actually the very first thing I want to do is go to... what do I want to do? I want to do some tests here. Well, I guess for the nuclear repulsion at least, we can just do our tests. What? Oh, duh. Oh. Did I actually mess something up earlier? So since my video earlier today, I fixed some clippy lints, and it looks like I may have messed up something. Let's see. How many? Oh wow, a bunch of stuff failed. That's strange. Wow, that's a big difference too. Let's see. What did I do? Oh. Yeah, I thought I figured out. Maybe some of you have seen the video I posted earlier today, where I was trying to fix this clippy lint, and I thought I was so smart after the video. Oh, it was warning me because this index is only used to index pairs, so I should just iterate over pairs. Obviously that was wrong, because I think pairs includes the virtual orbitals, when we only wanted to loop over the occupied orbitals. Okay, so I'm going to have to revert this commit for breaking it. Okay, and now let's make sure that that actually does pass. Okay, yeah, so that's I really need to look into some CI setup for running these tests automatically. Obviously, I didn't even think to run the test after that change, which is why you have tests in the first place, I guess. All right, let's add clippy test just to get that out of the way. Okay, so with that done, let's hop back over here, and I guess we'll just follow their nuclear repulsion energy. Eventually, I'm going to add a test. I'm going to add a module for this. And that's probably not exactly what we want to do, but what's this? Okay. But that's what I'm going to do. I'm going to add a module for this kind of test, just for convenience for now, and then eventually we'll work on the organization once we get it working. Okay, but first of all, we got the nuclear repulsion energy. We already know how to load a molecule. So let's just say this is molecule. Okay, so we're not going to do this anymore. What we're actually going to do for I in I have to remember what we have on molecule. So the idea is basically xij. So this is actually mole of I minus mole of j. So we can do it like this. Let xij, yij, dij. Actually, I think we can just do L2 norm. Is that the square root of the sum of the squares? Norm squared. Square root. I don't think it's quite right. Dot. That might be right. Oops. Come on, jump me back. Oh god. Wow, how do I get so lost? Nuclear repulsion. Okay. Wait, why is it I-32? Okay. Cannot index into a value of type. Right. Let's see. Yeah, I know you can do stuff like that. Let's try to do it with iterators. Let AI equal for AI in mole.atoms. So this is where we should probably implement iterator. Let's see, simple iterator for molecule. But I've had some trouble doing this before. This might be an absolute disaster. Let's see. I always forget how to do this. Impl iterator. And I don't think I can, yeah, you can't click links in here. Rust by example. Okay. Yeah, I think we want to impl into iterator. Yeah. But I want to borrow it. That's the hard thing. I think, yeah, I think we want to impl into iterator for ref molecule. Yeah, hold on. Okay, this, I think this is right. Atom is going to be a ref atom. Oh, geez. Tick A. It needs to live for as long as the molecule. Okay, and then into iter has to be an iterator. I'm not going to try this for too long. Standard vac into iter. Yeah, because I've tried this before, and completely messed it up. So, self item. It's looking okay so far. Yeah, but then, yep. Oh, atoms? Yeah, oh, of course. Yeah, this is exactly what I ran into before. Oh, do I have to do, okay. We want to borrow it. Oh, God. Standard slice. Okay, let's try that. Standard slice into iter. Alright, what did it say? Hold on. Oh, just iter. Standard slice iter. Tick A, self item. Oh god. Yeah, see, this is what I've run into before. So obviously I just don't know how to expected struct. Let's see. Implement into iter for reference to collection. I guess I should just look in the iterator. Oh. Wait, is this all I need to do? Okay, let's go back to trying iterator. This feels pretty embarrassing, but I've got to figure this out at some point. It's just so nice to be able to loop over your own stuff. Oh, whoops. Alright, item is impl iterator for, oh. Item equals ref tick A atom. Okay, let's give that a try. No, this isn't generic. Okay. Is not constrained. I guess we have to do it like this. Okay, to do. Self dot atoms dot next. Okay, does that work? In mold. Does it work? Oh, wow. Let's see if this works. Of course. Oh. Perfect. Fail our test. Expected strike. Okay, yes. Great. Oh, this is a potential issue, definitely. Oh my god, I forgot to change the scene. Well, that's pretty funny. Sorry about that, guys. Well, anyway, what I was saying earlier. Wow, I guess I'm gonna cut the video here. Wow, yeah, I'm gonna have to cut off the beginning part of that video. So the point today is we're looking at libint, and we are trying to integrate this with the Hartree-Fock code we have in our code. So as you'll see over here, I have the libint code pulled up, and we're kind of going through it, trying to use some of it over here. So anyway, what I just realized was that potentially these nuclear repulsion energies from the Crawford programming project could possibly not actually agree with the geometries in those projects. So we're about to figure that out. So we are going to call nuclear repulsion, but we're going to be calling geom.dat test files H2O STO3G geom.dat. Okay, and then we'll pass in mol here. Okay, let's see. Well, we're going to get 0, of course. This is still running. Well, I thought I was so cool with my my scene set up on OBS, but I forgot to change the scene for the video. So sorry about that. Well, at least it's only about 18-20 minutes. Why is this running? Oh, it's doing it on each... Wait, what? Why is this getting called so much? What did I do? Oh! Oh, it never advances! Oh my goodness. Oh wow, I made an infinite loop. Okay, well that's obviously not right. Molecule. Okay. Wow. Alright, forget it. Forget it. Screw it. We're not doing it. Pub. Alright, and mol.atoms. Yeah, okay, hold on. Okay, we'll just run this test. Great. Okay. Yeah, very nice. I think, what is it called? Unit? Something like that. Are these methods on something? Molecule. Let's see, molecule. Maybe we only want unit. Yeah, where is this? Oh, return the unit vector in the direction of V. What the heck? What is an atom? Chord? Oh, jeez. What a mess. Alright, so these are the atoms. Dot chord minus aj dot chord. And these are probably private. Yeah. Alright, we're going to make them pub. Probably this should just be pub crate. Okay. Wait, why are there so many again? 1, 2, 3. Oh, duh. Okay, there should be, what, 6, I think? Is that right? Are there 6? 1, 2, 3, 4, 5, 6. Yeah. Makes sense to me, I think. Okay. Now we can get to what I was saying earlier, xij. Okay, so I think we can actually just... We need to... So we're just dotting these together. ai.chord dot aj.chord. And then we're taking the square root. Okay. So we have to borrow it. And then atomic number. Yeah, you just multiply the atomic numbers divided by r. Okay. What did I call it? My goodness. Oh. Atomic number times as of 64 times aj dot atomic number as of 64 over r. Alright, let's see if it works. Oh boy. Okay. What? Oh, it's negative xij. Oh, no. I messed this up. Hold on. I see. I think this is the norm. Isn't it the norm? Okay, now we got 0. Do I have to skip I plus... Is it skip I plus 1? Skips the first minutes. So if I is 1... Oh, yeah. Okay, I just skip I plus 1. This is why I'm always hesitant to use this kind of iterator thing, because I forget... Hey, that looks pretty good. Okay. That looks close enough for me. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, yeah. Diff EQ epsilon equals 1 e minus 12. That'll work for me. Beautiful. Okay, so now we actually do this from that. Now let's see if this fails any of our other tests. If that difference is enough. No? Okay. Great. So there's our nuclear repulsion energy. Let's make these pub crate, I guess. Does everything still compile? Great. Same thing here, I guess. Okay, pub crate. Looks good. HF. Great. That's really the only place we used. Wait, what? How is this not used anywhere else? Okay. What? Did we just pass it in or something? What's going on? Oh, I think I skipped that part of the Hartree fly. Okay, that's fine. Okay. Great. Compute nuclear propulsion explicitly. Great. Let's go back over here. So we are done with this. Now we get to look at the actual interesting part where we're creating a basis set. Now I'm like paranoid about the scene. Okay. You guys can see the scene, fortunately. Alright, so it might be time now. How do I want to do this? I think what I'm going to do, this is a little goofy, but HF libint. We'll just call it that. HF libint. And we'll just do the same thing that they're doing. So the reason I'm doing this is because I want to be able to run this code directly. Yeah, maybe this is dumb. Maybe I should make like maybe I should make a separate binary for it or something like that. But I really like this idea where I just write this test. I'm going to write all of the code inside of this test so that I can run it with my existing recipe. So this is how we're going to run this. Yeah, save it, of course. And it's not really a test, but whatever. All right. Let mole equal molecule load. So we'll do the same thing we did in that mole test, I think. My goodness. Okay, here we go. So that's the one we're going to use. We'll call it Enoch. And now we're actually ready to move on. So I can debug Enoch just for fun. Great. Alright, now we can dive into making a basis set. So we've got this shell thing. We've got these values. Yeah. So earlier I was looking at this shell thing, trying to figure out how it works. And this is where my inexperience with C++ I think will really come to light. Because I have no idea what this constructor thing is doing. I mean, I have some idea, of course. Actually, it kind of looks like... it looks more like Go than it does like Rust, but... Shells, I mean, I know that we're pushing a shell. I just don't know where the constructor is defined in C++. I find it really hard to read these class definitions. I've even noticed that watching some of John. Oh man, I should have looked up how to say his name. I'll just call him John Hook. That's what his website and everything is, or his Twitter handle. Watching some of his videos where he's porting C++ code, it's like these are just nightmares to look at. I have no idea. And this is the documentation. Oh, okay, this is how I make the shell. Ah, I see now. The contraction coefficients, the unity normalized primitives. Yeah. Here's like a cross-reference. Okay. Struct contraction. Shell default. Const shell. Shell. I think these are all of the constructors. Is that right? You can call it like, are these like overloads, I guess? You can call it with no arguments, you get the default. You call it with another shell, you get default. Other move. Okay. Cool, I guess. So I think this is what I want. Yeah. Okay, I am assuming this is what I want. So you call it with, what is an S vector? Oh goodness, small vector. Boost small vector, okay. Okay, we've got a vector, alpha, contraction, standard array. What is an array? Standard container for storing a fixed size sequence of elements. Wow. Why don't... Okay, I don't know. Oh, and then we have a default. My goodness, this is crazy stuff. I've never written C++. Wow. Okay. Sorry about switching the screen all the time. I only have one monitor here. Embed normalization. Alright, so where we're calling it, what do we do? Okay, it defaults to true. So we're probably going to have to do this renorm function as well. Goodness. Update max ln coef. Okay. Well, we'll cross that bridge when we get there. Well, I guess we're going to follow what they're doing. I guess I'm going to make this a module too, aren't I? Okay. Alright, and then I'm going to relocate this module to the lib. Does this compile? Yeah, it's not super anymore. Yes. Alright, here we go. Now we can do it. So we're going to have instruct shell. It has an alpha, which is a vet f64. We're going to have whatever a contraction is. And then we're going to have whatever O is. My goodness. I'll call it O, and this is going to be, well, I better call it little o. So this is a 3. Really? Oh, I think I got this backwards, didn't I? And this will be the embed thing. Okay, yeah, I have no idea. Let's see what a contraction is. A contraction. Oh, that's what this was. How do we build a contraction? Int L bool pure S vector coa. What does it look like when you use it? Okay, so this is the alpha. This is the contraction. Okay. Okay, great. Yeah. Struct. Oh, can I have it generate it for me? No. Struct contraction has L. It says int. I'm gonna go with usize. Pure bool and coef vec f64. Cool. The implement equal. Cool. Cartesian size. I guess we can do this real quick. Impl fn Cartesian size. There's a size t, which I think is a usize, right? L plus 1 time. Yeah, I guess this is const. Self dot L plus 1 times self dot L plus 2 over 2. Regular size if self dot pure do 2 times self dot L plus 1. Sweet. Alright, there's contraction taken care of. Now we'll go back to the shell thing. What is this? Maximum Ln of absolute contraction. Other. Oh. No, we're looking at this one. Yeah. Right? Alpha, this is the contraction, and this is the O. Whatever O is. O, origin. Okay, we're gonna go ahead and call it origin. Alpha, contour, origin, max Ln, maximum absolute contraction coefficients. How do they get? Oh, you get it like this. Real T. Oh, it's an array. Wait, what? Hold on. Is this an array of arrays? Struct array. My goodness. Okay, standard array. Standard array int 3. Why does it look like this? Here's an example of how to create an S plus P shell. Why does it have two sets of braces around it? That's what I'm wondering. Standard array. I don't know. Double braces. Oh. Okay, yes. I remember the documentation does say that it's C++ 11. Okay. So that makes sense. Double brace is required. Okay, whew. Okay, that was very confusing. I was like, is it an array of arrays? Let's see if do they actually use the double arrays here? They do, yeah. Origin. Okay, cool. Contraction. Okay, so we are building a Sto3G. Make Sto3G basis set. We're just gonna copy them. Make Sto3G basis for a molecule. This is going to return us a back of shell. Okay. So this is pretty nice so far. Because basically we just have to plug in numbers. These are just, we don't really have to do anything with these structs, except they're just containers for data right now. So we're just gonna fill them with data, and then at some point we're gonna have to figure out useful ways to access that data. But yeah, for now, no problem. 4 views. All right. Okay, make this. Guess we better Sto3G basis set. Site. Okay, hold on. Format. Oh, it didn't format that one. What? Libint. Great. Shells. All right. 4 atom and mol.atoms. Atomic numbers. So we can get kind of cute here. Do we need the, yes, we do need the chord actually. Maybe we want to use vec3 for this. since that's what we're using for these coordinates. Okay. Push. We're going to make a constructor for this. Impl. Yeah. Okay. Contraction 0. S shell. L is 0. Spherical is false. Wait, that's what the Boolean is? Pure. Spherical. Angular. Momentum. Spherical. Contraction coefficients. And what is alpha? Exponents of the primitive Gaussians. Great. So, fn new. We can just generate the new, I guess. Generate new. And then we'll generate a new for this as well. This might be a submodule at some point. Yeah, I'll take take this from John's book and just write a bunch of code, and then we'll test it at the end. For atom in mole atoms, we're going to do shells. Oh, well, we need to match mole dot atomic. We need to match atomic number. Yeah, obviously. All right. 1. This is hydrogen. Let's see, I think we're doing water right now, so let's just go with 8, I think. 8 to do. Anything else? Panic, unsupported element. Great. Okay, so we actually push. Yeah, we could do this. This would be pretty nice as a flat map, wouldn't it? Because, yeah, it's whatever. We're just gonna extend. Okay. Shells dot extend. Shell new vec contraction new 0 false vec. We actually don't want vec there. And then the origin is port clone. Do I not have to clone it? Using clone, which implements copy. Wow. I didn't know. Is implements copy? I guess that makes sense. Does an array of 3 floats implement a copy like that? Okay. Yep. There we go. Alright, there's our first shell. Here goes our second shell. Now, one issue I want to point out with looking at libint like this is that I did try to build it earlier, and it didn't go that well. Well, I mean, I guess it went fine, but I haven't actually like run it yet. So what I've done in the past when I was translating Fortran code is that I would step through them in GDB, and I'm kind of afraid I'm not going to be able to do that here. But maybe. We'll make this oxygen. Okay, and let's do hydrogen. Hydrogen's pretty easy. I'll try copying theirs this time. Shells.extend. Shell new. YC with this. What? Let's see. What is it? Evil surround. Edit. YSS curly brace. What? Okay, that's how you do that. YS curly braces with no. Evil surround change. Oh, it's not bound? What just happened? I don't know. Evil surround is a cool idea, but I have a lot of trouble actually using it. Okay, contraction. This is contraction new. Okay. Origin coordinates. No, this is just chord. And in this case, we can just push, actually. We'll just push instead of extend, because it's just one. Okay, great. So that's a Sto3G basis set, I guess. Yeah, return shells. Okay, that was actually easier than I expected. Oh, wait, hold on. I forgot to actually do the rest of shell. Shell new. So we get all of this stuff. Okay. So we have to... yes. I really don't want to give it such a long name. We'll just call it embed norm. Now... when we're in here, they don't pass a fourth argument. Okay. Shells. Okay, hold on. They don't pass another argument, which means we'll take the default argument. The default is true. which means we're going to pass true when we call it. Whoops. True. Okay, and when that's true, we need to do something else. We need to call renorm. Embeds normalization constants into contraction. Ah, do this before computing integrals. Okay, it's private, so I guess I'm gonna do it like this. Ret dot renorm if embed norm. Ret dot renorm else. What do we do else? Update max ln. So that's supposed to be. That's a field, right? Max ln. Oh god. As a contraction, alpha max ln cof. Maximum ln of absolute contraction coefficient for each primitive. And we call it max ln cof f64. Oh, s vector. That. These might be dvex, I just realized. This one and alpha might be dvex, but we'll see that later. Okay, ret.renorm else we call update max ln coef. Update max ret.update max ln coef and then return. Okay. Wait, what am I doing? No, this just needs to go down here. And we're going to pass these like this. What's the problem? What? Help add semicolon here. Oh, whoops. Okay, and then we'll see what renorm and the other guy need to take. Yeah, this one is, it says void, but it's not really void. Due to dfk-1, a 64-bit integer type. Kind of ridiculous restriction anyway. Square root pi cubed. Wow. Okay. What is... auto C... We're going to loop over the contraction. Oh, goodness. Auto C contraction. What is a contraction? Okay, I guess we're looping over the coefficients. What is this? Oh, it's a vector of contract. Wait, am I dumb? Hold on. Oh, it's a vector of contractions. Hold on. Wait. What? Okay. Let's get back over here. Shell. Wait, but there's always only one contraction. Oh, for Sto3G. Okay, I see. P shell L equals. Wait, did I even do that right? L equals. No, I did not do that right. Okay. Did I get this one right? 0 false vec. Okay, that one looks fine, but we need to fix the oxygen one. Yeah, because this one, alright, we got 130, 23, 6, 0 false, this. 0 false. Oh, maybe I only got the last one wrong. This is supposed to be 1, because this is the P shell. False, false, false. Okay. Good. I think that's fixed. It's just now I need to fix this. Because it can be a vec. Vec of contraction. Like that, right? Great. Okay. Unit normalized shell. Oh man. Now we can take a look at this. Where do we go? Max ln cof. Let's do renorm first, I guess. For C in contraction. So this needs to take the contraction, takes alpha, we better put them in the right order, right? Alpha, contraction, 2 alpha, normalization factor. Do enforce unit normalization. What does that do? Decal type. Difficult or impossible to declare. Wow. Gamma, alpha, norm. I don't know what this is. Oh boy. What? What is that? DFK minus 1? Oh, factorial. Oh, wow. 1, 1, 1, 2. Wait, what? Okay. Double factorial. Wow. Double factorial. Okay. Interesting. Never heard of that before. P equals Q1, otherwise 2. DFK minus 1. Wow. Well, I guess we'll just copy that. Fine. it looks like we only need alpha. I don't, do they use the origin anywhere? Oh, no. Origin. I'm guessing you just keep the origin around for later. Well, anyway, let's just start writing it and see what if it pops up. So it looks like just this. And the reason I'm writing it like this is because I'm going to ask it to generate the function for me. Yeah, there we go. Great. And I mean, I'm assuming that it gives us update. Okay, we end up calling update max ln, wherein we use. Am I setting it anywhere? Okay, and in here we're going to call it well, let's see what it requires. Max len coef, or I think it's log. I guess it's max log coef. Max log coef resize to n prim. What is n prim? Alpha dot size. Okay, so we definitely need alpha again. And it looks like we need contour. There's gonna have to be references too. Does that mean that this is the negative? It's the negative maximum float? Documentation? Oh. Well, that's hilarious. They just set it to the smallest possible number? Why don't they use min? Is there not min? Ah, okay. I see. Numerical index. Okay. Okay. I guess that's one way to do it. Okay. Yeah, I mean, usually you just initialize it to the first value, right? But I guess... I don't know. Okay. I mean, it certainly works. Pretty funny, though. Okay. Now we can generate this. Okay. And at the end of this, we call self update max with alpha contour. But first we have to do some work on alpha and contour themselves. Now, I think... Oh yeah, this is supposed to return a vet F64. Of course. Oh, and it, I see. Oh, right. Yeah, these are going to be moved, so this needs to actually take vec. Let's start this. No. Not this, plus, followed by this. We want to capture the stuff inside. I am so tired of writing this. And we'll replace this with this. And backslash. And I forgot this. No. Oh. I forgot the G, but it still works. And, okay. Now we will return a vector. Why are you mad? Oh, because now I have to borrow them. Borrow a moved value. Okay, fine. Fine. There. Wait, you don't have to put them in the same order, do you? I can probably just move this. Okay, fine. Okay, compiler. I kind of wish you could have done that, but whatever. Cool. Renorm. Now we have to actually implement renorm. Okay. Although this looks a little easier. Max ln coef. Resize. So in prim is number of primitives is just alpha.size. I am going to call it red here because, oh whoops, I'm doing this in the wrong one, equals vec with capacity and prim. Okay, there we go. For P. Not equal in prim. Wow, P not equal. It's so weird not to use like less than. We're not changing alpha while we iterate, right? P and alpha plus P. Max ln coef. Oh god, that's a vec. Oh, I knew that. I think maybe we don't want this to be with capacity. I think we want 0.04 in the prim. Like we're going to create it with that length. Whoops. Vec. So for, I think I can just do P in red, right? Max ln C. I mean, we're just going to set it equal to contour 0 dot abs dot log. Oh, dot C dot coef doesn't have, oh whoops C of 0 dot coef. What did I call it? Hold on, I'm gonna go see what I actually did in contraction. It is coef. Oh, coef of P iter mute dot enumerate dot log. Oh, it takes the base, I guess. Is there an ln? All right, now let's find out if this is what base this log is. Log. The natural log. Okay, so we definitely want ln. Natural logarithm. Okay. Okay, max, let mute max log c be the first one. Okay, I mean, but surely there's at least one element in the contraction, right? Like the only reason I would do this is if that was actually going to be a valuable number. And I don't think you're ever going to want to use that number. And to do note, if there can be 0 contractions, you might want to initialize max LNC to minus standard numeric limits real t. I just don't think that that's relevant. I think there's always going to be at least one contraction, so this is a safe index. I don't know. I mean, it makes it slightly annoying because now I should loop over, like for c and contour.iter.skip 1, because I already set it to this. And if yeah, and then we set max LNC to max LNC dot max c dot cof p dot abs dot ln, like that. And then at the end, we'll set e equal max LNC. Great. Okay, so before that though, we have to come back to renorm. Const square root pi cubed. No. Whoa. Clippy will complain about this. Yeah. What is a real t? Double. Yeah, okay. Should be fine. NP is in prim. Wow. You can just type let and it just scoots you along a little. Yeah, so the sad thing, of course, is that I can't really test anything. I'm not really going to get to test anything. Oh, hey, Rare Tapes. I hope you're doing well, too. Wow, how'd you do an emoji? Okay, and we're also going to have to go grab this K minus thing. Which is why they had this goofy... Oh, here's the assertion. Yeah, assert c.l is less than or equal to 15. Yeah, so it's going to be a little bit hard to test this until we have it all put together. And at that point, it'll be difficult to debug it because we have it all put together. Yeah. But We'll see how it goes. If if we're having a really hard time, at that point I can always try to get libint running in the debugger. It might not be hard at all. I'm not really sure. I mean, really, if I go back to their, let's see, can I go back to this Hartree Fock thing? I'm just not sure about this make file. Check 1, check 2, test. I mean, it shouldn't be that hard. Make test 1. Let's see if this works. Oh, eigen. Yeah, I'm not sure about that. I think maybe I have to go up here. Build, test, Hartree Fock. This doesn't look like it's gonna work, does it? Yeah, nothing to be done. Not sure, but it's probably we can probably figure it out. Okay, I need to go back to shell. I'm in renorm. Great. Sure, we'll do the same. Assert c.l plus c equal to 15. Whoops. So probably we should be looping over P here, right? Yeah, let's go for it. For P in alpha. Assert P is greater than or equal to 0. Sure. Star P. If P not equal 0, we do something. Let 2 alpha equal 2 times P. Oh, right. Shoo. Alpha to AM32 equal 2 alpha dot pow c dot l plus 1. This is pow I as I size. What does this take? I32. Oh. What now? Oh, this is, okay, right. Why can't I do the cast after add one? Oh, because it was only applying to the one. Duh. Okay. Okay. 2 alpha pow I cl plus 1 times 2 alpha dot square root. Great. And then, okay, I'm just going to copy this one. let oh, this is funny. I bet there's no, I can't do like usize POW. Yeah, okay. CL is an integer, right? So it's 2.0 to the 2 square pi cubed. Oh. Times dfk minus 1. Alright, and then we're going to make a constant somewhere const dfk minus 1. No, not F64. What is, as long as I get a big integer, right? I think they're supposed to be F64s, right? 64-bit integer type. Okay. Oh, 64 by 15. How do I always get that backwards? Right. Oh, God. 31? Wait, why does it say 15? 31 lines? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, wow. Why does it say this? Due to kf minus 1, a 64-bit integer type. 31. Well, I don't know. Double factorial of k minus 1. Looks like a Christmas tree, right? Alright, here we go. dfk minus 1. This is, okay, as F64. Great. And then c dot cof of p times equals normalization factor. Great. I think you knew that, right? Yeah. Okay. Okay, so that should take care of that part. Close, close. Whoa. That closes the if, this closes the for. Okay, so we are still in this. Need to force, do enforce. Auto normalization. Defaultable Boolean? Oh, it's right here. False value 0, true value 1, default value 2. Wow. Okay, by default, shells will be renormalized to Unity. So I'm just gonna go with that. If true. Will Clippy get mad about this? I'm assuming it will. This should be do enforce unit normalization. Less than or equal to P. Let gamma equal alpha of P plus alpha of Q. Oh my. Alright, if oh yeah, it's supposed to be in parentheses. How I gamma c dot l plus 1 32 times gamma dot square root. Okay, yep. Now this is, I think, needs to be this. As of 64. Okay. If P is Q, 1, else 2, times df k minus of 2 times CL, as of 64, times square root of pi cubed times c dot cof P times c dot cof Q over 2 to the c dot L times pow gamma to the c dot L plus 1 times square root gamma. Okay, that looks right. We close the two for loops, or for. I usually just call it fac. 1 over norm dot square root See, if my coef here were a vector, I could just do the multiplication at once, but... Oh, wait, no, I see. Yeah, 4p is 0 to p. C dot coef of p times equals... Alright. Okay, close that for, close this if, close this for, if, and before. And then we call update. Okay, great. Embeds normalization constants into contraction coefficients. Great. So I think that's our shell, right? So now we have a shell. It has a vector of alpha, vector of contractions. It has an origin, or each shell has an origin. Okay. Great. I think we're back to make Sto3G, right? Shell. Okay, we got shells. Okay, make Sto3G basis should be good to go. Wait, Clippy. Clippy doesn't mind. Let me just make a test real quick, just to make sure I haven't broken anything. Oh, great. Let's see. I think that is a commit for sure. Wow. Initialize. I have no idea what this does. Let's see. Initialize. Manage singleton. Yeah, this is when it's going to get scary, I think. But we'll see. Bool. Initialize. Okay. Now ready to compute. If not initialized, using namespace detail initializer. Okay, so I think this is like a phantom data from Rust. But what is it actually doing for both successor? It doesn't look like it's actually doing anything. As far as I can tell, if not initialized. Manage singleton, instance exists. Okay. Okay. It doesn't look like it does anything, but I'm sure we'll find out later. But anyway, let's write this down. So what it's called? Sto3G basis. Make Sto3G basis. Yep. Alright, so it's untested, of course, but like I was saying, we don't know how to test it. Oh boy. Yeah, this is when we get into this engine thing. We've got an operator. I think the operator is just an enum. Okay. That might be it for today. How long have we been going? Almost 2 hours. Yeah, I think that's a pretty good stopping point for today. We can pick back up tomorrow, because tomorrow we're going to get into the real meat of it, I think, where we're going to actually have to look at this integral engine stuff, computes integrals of operators. Yeah. One body engine. Let's see, how long is this engine class? Okay, this is another constructor. Yeah, this is going to be the bulk of it, I think. So we'll see. We'll see how it goes. Compute one body ints. Shells operator. Well, you know what? I guess before... Let's take a look at this. I'm pretty sure it's just a simple enum. Yeah. There must be... Start with 0. Okay, we'll do the little operator enum real quick. And then I'm going to wrap up for the day. Enum operator, overlap, kinetic, nuclear, Coulomb. Oh, there's also a Coulomb. What else do we have? Coulomb. I guess I should use, let's see, projectile, multi-occur, operator. Oh, I think I actually just wanted occur, yeah, in this buffer. Overlap, kinetic, nuclear, Coulomb. Okay, so it looks like we got all the options there. Types. Operators supported by engine. Overlap. Well, we'll just copy their documentation too. Overlap. Electronic kinetic energy. Minus 1/2. Whoops. Oh yeah, tech. I don't think you can do frac with this, right? Minus 1/2 squared. Coulomb potential due to point charges. And then where's Coulomb? Coulomb. Two-body Coulomb operator. 1/R12. Did I put a space there? No. Why do they look so wide? Okay. Okay. Okay, yeah, now we've turned off the LaTeX stuff. Compute one body ints. Wait, when did we build the shells? Oh, right. Let shells equal make sto3g basis. One body integrals for shells with operator overlap. S. So we may be able to test this using just a quantum chemistry package. If I feed it this geometry, I'm pretty sure it will spit this stuff out. So I can just run a sto3g computation. Hartree Fox, sto3g. Yeah, we'll see what we get. Okay. So we may be able to take care of this. This is the kinetic energy. And then B. Oh, this is great. Wow. This might feed straight into our... Where is this? Do SCF. We might be almost done. Why is this file so long? 1 electron integrals. Where are the 2 electron integrals? Compute 1 electron integrals. Build initial gas density. I'm scared. Where are the 2 electron integrals? Wait, what? Oh wait, do we not? Each core will usually fail. Wait. Wait, isn't there a 2-body ints? There it is. Compute 2-body Fock. That's where the Coulomb integrals are. Okay. Okay. Yeah, that'll be the hard part, probably. This shouldn't be too bad. But anyway, I just wanted to check. Yeah, kinetic integrals plus attraction integrals. Overlap. Yeah, overlap integral. Okay, so there's all of that. So that's great. Wow. So, okay, no, we can test it. As soon as we get this 1-body integral function loaded, we can replace these functions with their actual, with this compute 1-body integral thing. Okay, so that's a lot. That's good. That's great. Okay, this is awesome. Yeah, so tomorrow we'll really be in business. This is really not as involved as I thought, as long as this engine stuff isn't too crazy. Yeah, it really just depends on this engine thing. Yeah. Cool. I mean, looking at it, it doesn't look that bad, but maybe it's pretty bad. Maybe it's pretty bad. Okay, hold on. Hold on, maybe it's pretty bad. Okay. Well, we'll dive into that tomorrow. Yeah, that's a problem for tomorrow. Libint. Where's... Alright, look, this is one thing that drives me crazy about Vertigo. Like, I type lib, and libint is nowhere to be found. It's like, then I type more of it, and it pops up. It's just unbelievable. Alright, the reason I actually did this is because I wanted to generate this function. There we go. Alright. There we go. And this is going to return, this is it's a whatever this is. I think it's a matrix, right? Yeah, matrix. D. Matt. To do. Great. Yeah, okay, we better make it one of these. We'll put these in. Alright. There we go. Add operator enum and set up for 1-body ints, 1-body integrals tomorrow. Okay, well, that looks great to me. Okay. Yeah, thanks everybody for stopping by. Good to see you all. I don't think anybody. I think nobody was here maybe when I was when I had just like a plain black screen. But yeah, the beginning was a bit of a disaster. I forgot to check that my OBS setup had swapped, or that my OBS scene had swapped when I thought it did. So I will not make that mistake again, hopefully. And with that, I'll see you guys tomorrow. So I mean, well, I guess I always do this, but I'm gonna ramble a little longer before I actually sign out. I am actually working on this during my normal work hours. So I'm just gonna be streaming during the day, working on this. So hopefully, again, if the engine thing doesn't take too long, that will only be a couple of days. But this is really exciting. This is fun stuff. Hopefully you guys will get something out of it too. Let me know if you have any questions or if I've left any bugs in the code, definitely. But, alright, with that said, I should see you tomorrow. See ya.